So finished with 3.5 yesterday. So today we will pick up with section 3.6 and continue the review. So in section 3.6 we were graphing rational functions. And with some caveats to it, some special cases. Essentially, rational functions that can be factored, whose numerators and denominators can both be factored completely into linear factors. More than that, things become a little bit more tricky to determine. So we had, was it 52 and 54 we handed in. Let's look at, say, 58. So graph y equals x squared minus x minus 6 and x squared plus 3x. Show clearly, label all asymptotes and x and y intercepts. Okay, so here the rational functions that we look at, okay, either the degree on the top is less than the degree on the bottom, or the degree on top and bottom are the same. If they're not, then you have to do a polynomial long division first, and then there's more to say after that. So degree 2 on the top and the bottom, in which case the horizontal asymptote is the ratio of the coefficients of the highest power of x. So horizontal asymptote here at y equals 1 over 1, which is just 1. Okay, if the degree on the top was less than the degree on the bottom, then the horizontal asymptote is at y equal to 0. So vertical asymptotes, well, first of all, we need to factor this in order to determine that part. So this is x minus 3 times x plus 2 on the top, and x times x plus 3 on the bottom. So the vertical asymptotes are where the bottom is equal to 0, which is at x and x minus 3, or x equal to 0 and x equal to minus 3. All right, that's where the bottom of that fraction is equal to 0. X-intercepts, that's where the top of the fraction is equal to 0, so that's at 3 and minus 2. And then the y-intercept, that's just where x is equal to 0. So you just set x equal to 0 in this equation. Oh, well, you can't have a y-intercept because you have a vertical asymptote at the y-axis, which is x equal to 0. None, because there's a vertical asymptote at the y-axis, right, at x equal to 0. Normally, you'll just plug in x equal to 0, and it'll give you that y-intercept. So this is the y-axis. Okay. So there's those 4 parts: horizontal asymptotes, vertical asymptotes, x-intercepts, y-intercepts. Now, I'm not going to give you such a problem, and we really didn't cover such problems, but when the top and the bottom of the fraction is equal to 0, then there's actually just like a little hole in the graph. But that's not something, we're addressing in this course. Okay, so from here, the only other property of the graph that we really need to know about is that it's smooth and continuous and doesn't wiggle around really. So I have vertical asymptote at the y-axis and at x equal to -3, so right about there. And horizontal asymptote at y equal to 1, so right about here. So this is x equal to -3, y equal to 1. X-intercepts at 3 and -2. So here's -2, and here's 3. Oh, and then we have to do the positive and negative behavior of the function. So before we draw, so let me do that first. I don't think these numbers here are working too well. Okay, so you put where your vertical asymptotes are, which is at -3, 0, and your x-intercepts, -2 and 3. So you've got these intervals to check for this factored function over here. So if you take a number less than -3, say -4, well, all these are negative. It's negative, negative over negative, negative, so the whole thing is positive. Crossing over from -3 to -2, so if you take -2.5, this one switches to positive, but the remaining 3 are negative. So the whole thing is negative here. From -2 to 0 at -1, no, sorry, it wasn't this one that was positive. It was this one that's positive. At any rate, still negative. At -1, these two are positive and these two are negative. So negative, positive, negative, positive. So it's positive again. And between 0 and 3 at 1, everything is positive except this first one here. So this is negative, and then past 3, all 4 of those are positive. Okay, so I mean it flip-flops negative, positive, negative, or positive, negative, positive, negative, positive. It's always going to alternate like that unless you start getting some squared terms in there. Okay, in which case there'll be one spot where it doesn't alternate. But that's the expectation here, is that it alternates, or that's the result here, is that it does alternate because there's no squared factors there. All right, so what's this going to look like? So it starts off as positive. You got a horizontal asymptote here and a vertical asymptote here. So it must be like this. Again, smooth and continuous, right? And then the graph is going to hug those asymptotes. But it doesn't intersect those asymptotes. You can never intersect a vertical asymptote. A horizontal asymptote, yeah, it can do something like this is a vertical asymptote here. It can intersect a horizontal asymptote, like it can do something like this. But the point of the horizontal asymptote is that as it goes out to plus infinity or goes back to negative infinity, that's where it hugs the horizontal asymptote. So you can cross, like in the middle, a horizontal asymptote. That's fine. It's just out towards the end, it doesn't. A vertical asymptote, however, you never cross. That's where the function is undefined. Anyway, so this is what the graph's got to look like, given these assumptions. Smooth and continuous and doesn't wiggle around much, and it's got to hug those asymptotes. It can't be curved that way, because it's going to intersect this, or it's going to start wiggling around this thing. It has to be curved like that, given our assumptions. All right. So positive, then negative and positive with x-intercept here, and then this is the vertical asymptote as well, so it's got to be doing like this. And it's got to have an inflection point in there somewhere. Where is that inflection point? Well, can't really tell. Okay? You need calculus for that. But it's there, because in order to hug a vertical asymptote, going downwards, it's got to be curved down. Going upwards, it's got to be curved up. So let's see if I can make a nicer looking thing here. Of course, this is awful looking. This thing is really hard to draw on because it is just so slippery and like overly sensitive. Much better. Okay, so it must look like that. But so since there's this change in curvature from curve down to curve up, there's got to be an inflection point somewhere. Although it's hard to say where it is. We can't say where it is at this point. And then past here, it's got a x-intercept there, negative and then positive. This is a vertical asymptote, so it's got to be doing this. Okay, so that's the graph of that function. So like on the homework problems that we had for this section, of those that handed the problems in, most people got these, pretty much right, like at least half, like really did them very well. So it's a lot of information to, keep straight, but a lot of people did, and I was, glad to see that. So hopefully I'll see the same on the exam. Okay. So section 3.6 is just going to be a graphing problem of that sort. Okay, so the 4 bits of information about the graph, or 5, I guess, that you're looking for to start with: horizontal asymptote, vertical asymptote, x-intercepts, y-intercepts, and this positive negative behavior. And then from there, you should be able to get a reasonable picture of what the graph looks like. And this is a more detailed picture than what you would get if you were to plug this thing in. Oh. There we go. So plot y equals x minus 3, x plus 2. Oops. Divided by x times x plus 3. Right, so it's kind of hard to get an idea of what this picture is trying to say here. It doesn't show the asymptote too clearly because there isn't enough range on the y-axis. Although it does show it. I mean, now that you know it's there, you have a better idea of what this picture is actually trying to say. Right? There's a vertical asymptote here, and also one at the x-axis, right? Here it's, I don't know why they gave this picture. But anyway, so that gives you a good idea what these graphs look like. All right. On to section 4.1. We've been talking about these exponential functions. So the graph of exponential function has got a horizontal asymptote along half of the x-axis. So, for example, like y equals a to the x for a bigger than 1, looks like that. And for a less than 1, looks like this. Well, for a between 0 and 1. For a equal to 1, it would just be a horizontal line, of course. And this y-intercept here is at 1. That's a to the 0. So, we did one problem where we were trying to graph such a function. So, let's say number 36. So y equals 5 to the minus x minus 3. Okay, how do we deal with this negative exponent, 5 to the minus x? There's a couple different ways to look at that. Here's one way to do it. So this means 5 to the minus 1 to the x minus 3. Right? Remember, when you have a nested exponential expression like that, you multiply the exponents. Okay, so I'm sort of undoing the multiplication here. 5 to the negative 1, of course, is 1/5. Right, so now instead of 5 to the negative x, it's just 1/5 to the positive x. Right, so this gives me the exponential function with a less than 1. So exponential function with a less than 1, and then we subtract 3 from it. So the graph of this function is going to look like this. Well, first of all, it starts out like that, and then I'm going to subtract 3 from it. So it's going to shift that asymptote from the x-axis down to the horizontal line, y equals negative 3, and the y-intercept from 1 to negative 2. So looking like this. So that is y equals the graph, y equals 1/5 x minus 3. Where's the x-intercept, by the way? Where's that x-intercept? How would we find that out? So in section 4.1, we hadn't addressed how to actually find that point, but now that we've been through the rest of chapter 4, we actually can. How do we find that point? Well, oops. What's special about that point? What's the y-coordinate of that point at the x-intercept? What's special about this point? What's the y-coordinate? So to find the x-intercept, right, set y equal to 0. Right, so 0 is equal to 5 to the minus x minus 3. Right, so bringing the 3 over here, 3 is equal to 5 to the minus x. So now how do I solve for x here? How do I solve for x there? Right, I apply a log function to each side, any log function. So I'll use natural log of 3. Now I can bring down that exponent. Like that, right? Using this natural log a to the r is r natural log of a, or, log base 10 of a to the r is r log base 10 of a. Right? I mean, either, whatever log function you're using, that always works. Okay, so that's why you apply that log function, is because it takes what is in the exponent, right? So you have this equation where your variable that you're solving for is in the exponent, and you want to get it out of the exponent. That's what the log does for you. So divide by negative natural log of 5, so natural log of 3 over negative natural log of 5 is equal to x. So that's where the x-intercept is, but we would like a better idea of what that number is. So 3 natural log divided by 5 natural log equals, so negative 0.6826. All right, so there's that x-intercept. So I actually didn't draw this graph steep enough, did I? I mean, if this is negative 2, I mean, it's more like right here. So negative 0.6826. So even that's not really, it should be even steeper than that. Exponential functions, the graphs are very steep. They are the typical example of a fast-growing function, exponential functions. Okay, so that's the graph of such a thing. And then, of course, we talked about, various modeling situations in which they use exponential functions. The sort of, most quintessential example is this compounded interest situation. So like in number 59, $500 is invested at 3.75%, compounded quarterly. Right? How much is the investment worth? After 1 year, 2 years, 10 years. Right, so this uses that compounded interest rate formula, which is an exponential function. I is your initial investment. 1 plus interest rate as a decimal over the number of compounding periods to the nt. So n is number of compounding periods per year. T equals years. I equals initial investment. And R equals interest rate as a decimal. As a decimal number, right? I mean, when we say 3%, we mean 0.03 as a multiplier. Right, 3% is a labeled term, right? So it's a number that comes along with the labels. Like, I mean, if I said 3% and 5%, you know, if you added them together, you'd get 8% or something like that, if that made sense in some way. But when you have two labeled quantities with the same label, you can add them. But like two labeled quantities with different labels, you can't add them. I mean, you can, but it doesn't mean anything, right? I mean, like three apples plus 2 bananas doesn't equal anything. It doesn't equal 5 of anything, right? So when we mean write R as an interest rate, the interest rate as a decimal is like this, 0.03. It's not a percent, it's just the number, 0.03. So just the difference between labeled and unlabeled quantities. Okay, so in this situation, the amount that it's worth after 1 year is $500 times 1 plus 0.0375 over 4 to the fourth. After 2 years, 500, 1 plus 0.0375 over 4 to the eighth. And A of 10, 500 times 1 plus 0.0375 over 4 to the 40th. Right, so So 500 times 1 plus 0.0375 to the fourth. Oops. So 519 and 2 cents. Of course, when you're talking about dollars and cents, you can usually round off to the nearest penny. So after 8 years, 538.75. And after 10 years, 726.22. All right, and you know, one of the more interesting, the more interesting sorts of questions that one can ask, are the following: how long does it take for the $500 to grow to 700? Right, so here is where we do some solutions to some equations that we need to solve, and that include exponential expressions. So in this case, I mean, we know it's less than 10 years, right? Because after 10 years, you get this much. So we want the amount to be 700. And we started out with the 500. And we want to solve for t. All right, so 7/5 is equal to 1.0375. No, 0.0375 divided by 4 is that plus 1. So 1.009375 to the 4t. All right, so we take whichever log function of both sides that you'd like to use. And then that brings the exponent in this exponential expression out front. So natural log 7/5 is equal to 4t times natural log 1.009375. Doing the division, natural log 7/5 divided by 4 times natural log 1.009375. So that's the number of years. So natural log 7/5 divided by 4 times natural log 1.009375. So 9.01 years. So is approximately t. Notice, right, that answer makes sense. You know, that is our expectation, right? We looked at, you know, the growth of that investment over, you know, some number of years, 1 year, 2 years, 10 years, right? And we see that at 10 years it grew to 726, and after 2 years it was like 538. So we expect that the value of the investment reaches $700, right, before 10 years, right? Somewhat close to the 10th year, but before that. And the answer we came up with here is 9.01, right? So that makes sense, you know, that's what our expectation is. You know, that's not a check on the exact answer. There still might be some, you know, some kind of little error in here that was made. But at least, you know, I mean, you didn't come out with like 18 years, right? I mean, if you came out with 18 years, you know you're wrong, right? You know there was a mistake made. Or if you came out with like 2 years, you know that there's a mistake made. Okay, so you know sort of some approximate range of where the answer should be. All right. Section 4.2 is really the same as section 4.1, except you know they're talking about the exponential functions base e, the natural base. Well, let's take a look at a problem in here. So number 30 in section 4.2. So for a certain type of tree, The diameter in feet depends on the tree's age according to this logistic growth model. So it's saying that the diameter of a tree in feet is 5.4 over 1.2.9, 1 plus 2.9 e to the minus 0.01 t. So t over 100. So this is equal to the diameter of a t years old tree of a certain type in feet. And this is a logistic type function. It's got a growth, with an upper asymptote. So let's see, 5.4 divided by 3.9, or no, 5.4 is the upper asymptote. And so it's a growth model looking like that. And at 0, what is it at 0? It's well, I mean, of course, obviously this is not quite right. I mean, it's just an approximation of some sort, because at like 0 years, right, like right as you plant the tree, the diameter is 5.4 divided by 3.9, which is a positive number, which is nonsense. I mean, of course, this is just an approximate model. But a logistic type function grows like this. Okay, so it has this upper asymptote, and it grows towards that. Or that's asymptotic growth. There can also be, logistic growth. There's also logistic decay, which looks like that. What is the diameter of a 20-year-old tree? How about 40-year-old? Okay, well, let's check those out. So 5.4 divided by 1 plus 2.9 times e to the minus, so 20-year-old tree. Oh, it's 0.2, not 0.1. 0.2. So 20 times 0.02 is 40, so 0.4. What happened here? 2.9 times... Oh, right, because it's got the negative exponent there. That's why I did that. So result, 1.834 feet. So the diameter of the 20-year-old tree, so you put 20 in here, and it gave us 1.834 feet. The 40-year-old tree, so 40-year-old tree, so for 40, that's going to be a 0.8 there. So 2.344. I was thinking that that might be closer to the 5. Let's do a little bit more than that. Let's say 100-year-old tree. So 100, so that's going to be 100 here, which is just going to be e to the negative 2. Well, still not very close, is it? 3.87. Huh. 3.8799. Okay, so that was 100. Well, as I was saying, with this logistic model, you would expect sort of this upper limit of 5. But we aren't getting too close to it too fast. I mean, at 100 years, it's still only that much. So, well, how long does it take to get, so let's ask this question. How long, so how many years until the diameter is 5 feet? All right, so rather than just plugging in values for t to see when we get close to 5.4, I mean, let's just solve directly. Right? How many years does it take for the diameter of that tree to reach 5 feet? So 5 is equal to this. Solve for t. Okay, so this one's a little bit more involved than the other equations, but still we've solved stuff like this before. So think of this as 5 over 1 equals 5.4 over 1 plus 2.9 e to the minus 0.02 t, like that, and we'll do that cross multiplication. Well, actually, I'm going to move this over here and then divide by 5. So 1 plus 2.9 e to the minus 0.02 t equals 5 over 5.4. Okay, so let's forget about this one. I guess that's not necessary to look at. So what I did is I took the denominator of this fraction, multiplied both sides of the equation by that denominator, 1 plus 2.9 e to the minus 0.02 t, and divided both sides by 5. Oops, this is upside down. Divided both sides by 5. So, no, it was correct. 5.4 over 5. So 5.4 over 5 is equal to that. Subtract 1. 5.4 over 5 minus 1. So that's 0.4 over 5. divide both sides by 2.9. So e to the minus 0.02t is equal to 0.4 over 5 times 2.9. 0.4 divided by 5 times 2.9. So 0.027586. Okay, so let's take a look at that again and talk about what we're actually doing here in solving this equation. So here is a logistic growth function, and we want to know when it's equal to 5. So I took the denominator, put it over here, and took this and put it in the denominator there. I divide both sides by 5, multiply both sides of the equation by this expression, and I get that. Subtract the 1, and I get this, and then divide by 2.9, and I get that. So the point of this that I was doing was to solve for the exponential expression. Right? I got e to the something t equals a number. E to the something t equals a number. Now I can apply the natural log. So since we're dealing with base e, it's nice to use the natural log because instead of just bringing the exponent down, I mean you can use that you can use that rule from before. Natural log of a to the r is equal to r natural log of a. But when the base is e, natural log e to the r, it's just r. Because the natural log of e is just 1. Right? So the natural log of e is just 1, so the e just disappears. So it's minus 0.02t is equal to natural log 0.027586. Divide by negative 0.2t, or negative 0.02, 0.027586. 586 divided by negative 0.02. So is the answer negative? Is the answer negative? Looking at that. Right, I mean, we're dividing the natural log of this number by a negative 0.02. Is that going to give me a negative answer? Well, no, because this number inside the natural log is less than 1. Right? This number is less than 1. So the argument of a natural log needs to be positive. The domain of a natural log function is positive. But when the argument is less than 1, the answer is, the value of that log is negative. So we have log 0.027586. So I can do natural log of that divided by 0.02 is 179.52 years. The negative is there because I didn't include it in the calculation. So t is approximately 179.5 years to actually reach that 5-foot threshold. Okay, so it takes a while. All right. So section 4.3, we introduced the logarithm function. I mean, we were just using it here. The only problems in section 4.3 that we covered really was just using these laws of logarithms to do these expansions. So, for example, what are those problems that use the expansions? Where did they go? Oh, no, I'm sorry. No, this is just introducing the log function. The expansions are in section 4.4. 4.3 is just introducing the log function. In 4.4, so say number 44, so expand natural log 3x squared over x plus 1 to the 10th. So expand this completely. So in other words, use the properties of logarithmic functions to get all of the division, multiplication, exponentiation out of the argument as much as you can. So there was three rules for doing that. Not natural log, but any log of a times b is log of a plus log of b. Log of a over b was log of a minus log of b. And the one for dealing with exponentials, log of a to the r is r log of a. And this is for any base. So here with this one, natural log 3x squared over x plus 1 to the 10th. Starting out with that division, we can make it into a subtraction as such. All right, here we have a product, so we can change that product into a sum, like that. And we still have this. And now I've got these exponents inside the natural log expression, so I can apply that third property to bring those exponents down as coefficients. And that would be the extent to which you could expand that expression. So within each of these log expressions, the three log expressions here, there's no multiplication, division, or exponentiation within the argument that we can otherwise deal with. Now, there is an addition inside here, but there's no way to simplify log of a plus b. It's log of a times b that has this expansion. Log of a plus b, no, there's nothing you can do with that. Now, also, by the way, another sort of like warning, if you had log of x squared plus 1, you can't do anything with that exponent at this point, because that exponent is just over one term, right? The rule for dealing with exponents is here. Log of a to the r is r log of a. This is not log of something squared, right? The log of x plus 1 squared is equal to 2 log of x plus 1. That's fine. This is okay. Here, there's nothing that is squared. Not a whole expression that's squared. This is squared, but it's stuck within a, it's stuck within a sum. So you can't do anything with it. Okay. Right. So that's section 4.4. In section 4.5, we're solving equations that have exponential and log expressions in them. So we've done several examples of those already. I added them in our discussion of sections 4.1 and 4.2. But just a couple more here. Number 38. Solve for x. So here's another example of that logistic type expression model. So without all the funny decimal numbers, we have something like this. So 10 over 1 plus e to the minus x equals 2. Solve for x. Okay, let's take it a little slower this time. So 10 over 1 plus e to the minus x is equal to 2 over 1. So I'm going to multiply both sides by 1 plus e to the minus x divided by 2. Right, so that's going to move the 2 down here and move the 1 plus e to the x over there. So here they cancel, here these cancel, and I'm left with 10 over 2 is equal to 1 plus e to the minus x. So subtract 1 from each side. 4 is e to the minus x. Now I can apply a logarithm. So I've solved for the exponential expression. I've got e to the minus x equals e to the something x equals a number. So now I can take a log of both sides. Natural log is nice, right? Because with the natural log, the e just disappears. Let me get that. Right? Because natural log of x and e to the x are inverse functions of each other. Although you didn't have to use natural log, you can use log base 10. So natural log of 4 is 69.31. Oops, something went wrong there. 1.136. Right, or use log base 10, in which case log base 10 of 4 is equal to log base 10 of e to the minus x. So now we have log of 4 is equal to minus x log of e. So log of 4 divided by minus log of e is equal to x, but that will give you the exact same answer. So 4 log is that, divided by, here's my button for e, log equals 1.1362. Of course, it's negative. So you can use either log function. Doesn't matter. Okay. So it's 10:54. Okay, so we've covered most all of what the homework problems were. There's still some homework problems that we didn't have time to quite go over. Some types of problems, but solutions are online. I will work on getting the rest of the homework graded for you today. Other than that, I'll see you for the exam on Monday, and have a good weekend.